this. All right, so two example problems for kinetic and static friction. A child drags a heavy rubber-soled shoe by its laces across a sidewalk at a constant speed of 0.35 meters per second. The shoe has a mass of 1.56 kilograms and the coefficient of kinetic friction is 0.65. What is the force exerted by the child? Presumably, force exerted by the child on the shoe. Also, assume the shoe or the sole is in contact with the sidewalk, not bouncing around, and the child pulls horizontally, so like steadily sliding. So the first thing we're going to want to do is draw a free body diagram. Anytime you suspect that a problem has to do with Newton's laws, acceleration, force, mass, start with a free body diagram. So, shoe on a sidewalk. So we're going to assume that the sidewalk fully supports the shoe. That would be the normal force, sidewalk supporting shoe. Earth's gravity is pulling on the shoe with a force equal to the shoe's weight. Pull of gravity and weight are the same thing for us. The child pulls totally horizontally. So here will be the child's pull. I'll use capital P for pull force. And then there's friction between the shoe and the ground. So I'm going to call this F subscript F, friction, or we could call it F subscript K because we know it's kinetic friction since we know the shoe is sliding. Okay, so these are the forces on the shoe. There are four forces. I expect the normal force or the support force of sidewalk on shoe to be equal to the pull of gravity on the shoe. I expect the shoe to remain steadily in contact with the sidewalk, not bouncing around. That's sort of stated in the problem. So I expect normal force to be equal to weight, and I know that weight is equal to mass times acceleration due to gravity. So I actually know the quantity of normal force. The shoe has a mass of 1.56 kilograms, and acceleration due to gravity on Earth is 9.8 meters per second squared. So there's a normal force on the shoe equal to 15.288, so let's call it 15.29 newtons. We know the normal force. Now, a child drags a heavy rubber-soled shoe by its laces across the sidewalk at a constant speed. So this shoe is moving at a constant speed. That's important to know because if the speed is constant, that means the acceleration is zero. So since acceleration is zero, we know that the pull of the child to the right has to be in balance. Even though I drew them so they're out of balance, the pull to the right must be in balance with the force of friction. F net is equal to zero. So pull, which is what we're trying to find, is equal to the force of kinetic friction. I'm supposed to find the amount of pull of child on the shoe. What's the force exerted by the child? And I now know I can find that by calculating the kinetic friction force. Kinetic friction is coefficient of kinetic friction times normal force. I just found the normal force. Coefficient of kinetic friction for the shoe and sidewalk is given as 0.65. So we find that the force of kinetic friction between the shoe and the ground is 9.9372, 9.94 newtons, and that's equivalent to the pull of the child on the shoe because the speed of the shoe is constant and acceleration is zero. One more example problem, and you should be ready to do some practice on your own. So now, in the previous problem, if the child pulls with an extra 2 newtons, what will be the acceleration of the shoe? So now I imagine the shoe, or here we can imagine the shoe as a box. Either way, we consider the forces on the shoe, normal force, pull of gravity, child's pull, friction. We previously discussed how the normal force and pull of gravity are in balance. Oops, it looks like my camera froze. And so we knew that the normal force equal to the pull of gravity equal to the weight was 15.29 newtons. And then we found that the friction force, because we knew normal force, was equal to 9.94 newtons. Only now the pull force is not in balance with the friction force. Now the pull force is 2 newtons bigger. So 9.94 plus 2 more gives us a pull force of 11.9372. So let's go for 11.94 newtons. And now we're finding the acceleration of the shoe. So we no longer have the horizontal forces in balance. These two forces are out of balance. I have a pull to the right of 11.94 newtons and a pull to the left, or a push backward to the left, of 9.94 newtons of friction. So now the net force is 2.0 newtons. All right, 11.94 versus 9.94. And the acceleration of the shoe is net force divided by mass of the shoe. This is Newton's second law. 2.0 newtons divided by the mass of the shoe, which is 1.56 kilograms from the previous slide. And that's 1.282051282 meters per second squared. We round to 3 sig figs. Done. So now you're going to do some practice. You need to finish the Newton's Laws practice pages handout and turn that in today. It is due today in the inbox. Make sure it gets in the inbox with your name on it. I will be grading it for completion. You are checking your answers as you go with that set of problems. Once you've finished and turned that in, you need to start the Newton's Laws practice problems, which are on Canvas. I'm not printing copies of them, or maybe I'll print a single class set. But you're accessing these problems, practice problems, on Canvas. And again, you're checking your work as you go. Get as far as you can through that, and I'll start answering your questions and giving you some more example problems from that assignment when I see you again on Tuesday. Have a nice weekend. Bye.